Hi, everybody. Thank you for joining me today. My name is Nick DiVincenzo. I'm going to talk about what is new in SimCenter Test Lab durability analysis. I've got three main topics for today. So, one of them is the introduction of mission synthesis into Test Lab Neo. And then I've got two smaller features to discuss. One is create custom angles for the critical plane approach when looking at strain gauge rosette data for multi-axial fatigue. And then a nice little nifty feature. It is a 2D time at level display where we look at a time at level plot as a function of both that time at level and another variable. And I'll expound on that a little more with an example later in this webinar. But I'd say the main meat and potatoes of what we'll be discussing today is the implementation of mission synthesis in Test Lab Neo. It's something that we're very excited about. So just to start, I'd like to give everyone an overview of the mission synthesis procedure. So what is mission synthesis? What am I talking about when I say mission synthesis? It's an important part of vibration testing where we want to derive some sort of realistic vibration qualification test for a complex device under test mounted on a vibrating structure. All of these different components that we might design, we want to design them to meet a service life, and they may fail in the field due to a fatigue failure caused by vibration. So often the way that people will examine or test these articles is they'll use some sort of standardized PSD profile, and then they will shake that component on a shaker table using that standardized PSD profile. With the mission synthesis approach, we want to base that PSD profile on measurements taken in the real-life service environment of that component rather than using a generic standard. The idea being that these generic standards don't cover exactly what that part or that component is going to experience in the real world. So let's base this test on the actual vibration environments that part or component is going to experience in the real world. We're going to apply the principle of damage equivalence. So we're going to say, okay, we've taken some data. We can quantify that damage caused to the component using something called the fatigue damage spectrum. And now let's derive a PSD profile with the same damage equivalence as the real life data. And then what we also want to do is we want to accelerate this test. So you might say something about the service hour of your part or component. You might say, hey, we expect this thing to last 20,000 hours or 100,000 hours or a certain number of years. And we don't want to actually have to perform a shaker test for that long. So how can we accelerate this test and still maintain the equivalent damage that component would see in the field? And so to do these three things, we'll use the mission synthesis procedure where we will take some data on the component. We will calculate things like the fatigue damage spectrum. From that, we'll derive a PSD and we'll perform a shaker test. And we avoid using these generic standards, which may or may not be a good approximation of the real-life environment that your component will actually see. The mission synthesis procedure is laid out in 4 steps here. So starting with defining the missions. So this is where we need to define what types of environments our part or component will be exposed to in real life. So for an automobile, it might be accelerating, it might be braking, it might be a certain number of hours on one road type, it might be a certain number of hours at highway speeds, and so on. For off-highway or construction equipment, you might have a certain number of procedures for raising, lowering, hauling. In case of things like a dump truck, having actual debris or rocks or sand or whatever you're filling that truck in actually impact the bed of the truck and so on. And so these missions are making up the life cycle of the vibration environments that component is going to see. And we want to capture that vibration environment by taking data for all of those missions. So here we have pictured some data acquisition hardware from Siemens. We have the SCADAS RS, which is our ruggedized data acquisition system, as well as a SCADAS mobile here. And so we'll take this hardware and we'll go out and we'll acquire some representative data for all of those different mission profiles. Next, we need to analyze the damage potential of those environments and calculate the overall damage. And we'll do that using a function called the fatigue damage spectrum. So in TestLab, we've enabled the FDS, or we've implemented a fatigue damage spectrum and a maximum response spectrum calculation. We need to combine the fatigue damage spectrum and the maximum response spectrum. We need to combine them together for all these different events. And when I say combine, we combine these together in different ways. We might combine these in parallel. So, for example, if you're making your product for 2 different markets, you take data in both of those markets, but the product isn't going to actually see the service environments for both of those markets. It'll be one or the other. And so in that case, we want to envelope our fatigue damage spectra just to find the maximum damage it might see in either environment. And then if our part or component is going to see multiple of these environments in its service lifetime, we will add those fatigue damage spectra in series. And so we've added a kind of a nifty graphical way to do this in the software. So we'll be sure to show that. And then from there, we want to synthesize a accelerated PSD from the fatigue damage spectra. And this PSD will have a equivalent damage to the lifetime field data. And so we've implemented this in TestLab as well. Here you see the generic mission synthesis approach in TestLab, where we calculate the fatigue damage spectrum and the MRS. We combine those different environments together using this combination block, and then we synthesize either a PSD test or a swept sign test with a accelerated lifetime but a equivalent damage to those components. Got one more slide here before we jump into a demo, but just to expound a little bit more on the fatigue damage spectrum. Here I'm showing the fatigue damage spectrum from 2 different tests. One is a real test, so some accelerometer data taken on the dashboard of the vehicle, and the other is a fatigue damage spectrum derived from a ISO vibration profile. So the general idea being here, we can compare these 2 fatigue damage spectra, and I can see that the FDS of my measured field data is much lower than the FDS for this ISO vibration test, and that is true for all frequency lines. What I can conclude here is that the damage potential of this ISO test is much higher than the damage potential from my field data, and that might be good if I am aiming for a very conservative design approach, or I might want to consider testing my part with a less severe PSD, in that perhaps I'm introducing some failure mechanisms that my part would not normally see in the field because of how aggressively I'm testing it on the shaker table. But we'll use these fatigue damage spectra curves to compare the relative damage potential of things like different channels, different PSDs, or different events together. So let's jump into the software. I have a TestLab Neo project open here. And what I have in this TestLab Neo process is I'm going to split some data I have. So I have some time data and some PSD data. I'm going to take that time data, I'm going to calculate a fatigue damage spectrum from it. I'm then going to combine that data in different ways, both in series and in parallel, to reflect the way that the component will actually be used in the field. And from that, I'll calculate a PSD from the fatigue damage spectrum if I'd like the maximum response spectrum. So all of these methods here, besides the statistics method here and the split method here, are new in the 24.06 version of TestLab. I'm also going to take some PSDs and convert them to a fatigue damage spectrum. And what this can be really nice for doing is to validate some testing that you've done previously with different PSD profiles. So we can compare the damage severity of that old profile to the profile generated from the mission synthesis procedure. So first, let's take a quick look at the data that we are going to be using today. I have a number of different time histories corresponding to a number of different driving conditions for some display component in a vehicle. So this will be a little hard to see here. I'll maybe move this out of the way, but we have one run of data that is an uneven road in the Asia Pacific region, uneven road in the EU, uneven road in the US, going over some railway crossings, some highway measurements, and then some off-road measurements. And so I have, 7 different environments that are going to represent the vibration lifetime of this component that I'm trying to validate. And you can see some of them are much longer duration than others. Some of them are much more severe in terms of the magnitude of vibration. So if I split these out into different displays, I can see things like this uneven road and I would expect the railway environment here have relatively severe maximum vibration levels relative to things like the highway driving, for example. So the first step in the mission synthesis procedure is going to be, I'm going to take all of this data, including some PSD standards that we're going to take along for the ride here, and I'm going to replace it in the input basket. And then as a first step, just to show you this method, I'm going to calculate just up to this FDS and MRS block. In this block, I have a number of different properties, so I'm calculating the FDS. I'm going to choose to not calculate the MRS. I have some different cycle counting methods. Rainflow is the default. It's the one we advise most people use. We need to choose the minimum and the maximum frequency of our analysis, so I'm going to synthesize everything from 10 to 500 hertz, and then I need to choose a spacing on the frequency axis. I'm going to use a frequency resolution of 4 hertz. In addition, I need to choose the material data that I would like to use for this analysis. So when calculating a fatigue damage spectrum, we do a fatigue damage analysis where we cycle count these input time histories, we compare them to an SN curve, and then we use Miner's rule to accumulate damage. So in order to do that, we need to define a few material parameters. So I've got my sample material here. It has a Q factor or a damping of 10. And then I need to choose if I'd like a K value, an A value, and a B value. Now normally for K and for A, we can just leave this at the defaults at 1 for both of them. And then we need to choose the slope of our SN curve here, which is this Wöhler exponent B. And B is really the most important material parameter to set during this type of analysis. You may find in various literatures different B values to use based on maybe the material that your component is made out of. So whether that's aluminum, copper, or steel. For electronics, different values of B are preferred, and so on. So we're going to use this sample material. And kind of the nice thing about defining this in this material data section here is we no longer need to worry about carrying these material parameters through the rest of the analysis. The software is going to keep track of all of that for us. So I'll close this. I'm going to highlight this method and I'll choose check. And it's going to run this analysis up to and through the FDS and MRS block here. If I look in active analysis, for each of these channels that I selected, I have a fatigue damage spectrum. I'll expand this, and what I can get a good first glimpse at, or a good first look at by looking at these fatigue damage spectra, is which of these environments have the most severity. So I can see, for example, here in red, this uneven road Asia Pacific really does not have a large amount of damage potential. It may be evens out a little bit as we get into higher frequencies, but in the lower frequencies, it has much less damage potential than some of these other measurements like the uneven road EU, the railway environment, and so on. And so what this fatigue damage spectrum is showing us is the damage potential in that input time history at each frequency line in the analysis. I'll reject this. The next thing that we want to do after calculating that fatigue damage spectra is we need to choose how we're going to combine all of those FDS calculations together. So are they going to be in series or in parallel? I'll double click on this method here and I'll go to this combination area. I'll hit that ... and then any data that I have available in my input basket is going to show up on the left-hand side here. These are the measurements that I can choose to make combinations out of. These events can either be combined in series or in parallel. In this example here, this component is only going to be on a vehicle that's driven on a road in APAC, in the EU, or in the US. It's not going to be driven on road types for all three. So I want to combine these events in parallel rather than in series. And what that means is we are going to perform an envelope of the fatigue damage spectrum for all three events rather than summing them together. Likewise, we're saying this component is only going to be used on the highway in these two regions, either APAC or the EU and the US. So we will envelope these as well. And then I have environments that this product or component is always going to experience. And so we want to add all of those environments in series. So in summary, we're enveloping these three environments, we're enveloping these two environments, and then we are summing the envelope of this with the railway environment and the off-road environment. I enter the number of repetitions that I will go through for these time histories in order to reach my target lifetime for each environment. So here I could enter whatever number I wanted to. In this case, we've selected 4,200 repetitions of all of these environments except the off-road environment, which has 4,100 repetitions. And I would just enter that number of repetitions directly into the dialog box here. I'll hit OK. I'm going to give this a new run name, mission run, 8 hours. That 8 hours is a bit of a prelude. In this next block here, I choose the parameters for synthesizing my PSD from this data. I'm not going to use iterations. That's something that we won't touch on too much in this webinar, but it's essentially to try and get the final FDS result derived from the synthesized PSD to match more closely this combined FDS. If you have more questions on that, we can maybe take that discussion offline. But what I do need to do is I need to choose a total test time for this synthesized PSD. So in my case, I'm going to say I'm deriving an 8-hour test, and I'm doing so for the X, the Y, and the Z axes for this component that I'm testing. In this defined material, automatic is automatically selected. It's just going to carry forward the material properties that we defined in this FDS and MRS block. For fun, I'm going to then calculate the RMS from these PSD profiles. The RMS is often a quick sanity check indicator we can use to determine whether or not we've over-accelerated or under-accelerated our test. Finally, I've got this PSD to FDS and MRS block. I can use this to convert a PSD to a fatigue damage spectrum in order to compare something like a test specification or standard that I've been using to the actual field data. So in this block, we need to define the material data. So I've done that previously here. I just chose a default material with a B value of 5, so matching what I've done in this FDS and MRS block. And then I've chosen the same minimum and maximum frequency and the same frequency resolution. With a PSD, we need to give it a total time that PSD corresponds to, so I'm saying the input PSD corresponds to an 8-hour shaker test. I'll hit close here, and then I'll run this entire method or this entire process, and it's going to calculate the fatigue damage spectra. It's going to combine all those fatigue damage spectra together in the way I specified in this block here, and then it's going to calculate the FDS or a synthesized PSD from the fatigue damage spectra. So I'm going to click on this active analysis block here. I can see my process data results. So if I want to look at the FDS, the PSD, and the statistics for my display plus X, I can do that here. So on my left-hand side here, I see the PSD. I see the fatigue damage spectra. This is the combined fatigue damage spectrum from all of those environments. And then I have a nice little statistic table with RMS values. In TestLab, I can easily kind of get a look at all three axes by just control-clicking and adding them to these displays, and then I'll maximize this here. And so I can see very quickly that the synthesized PSD in the Z direction has an RMS value of 3.58. So it's got the highest RMS. I can kind of visually see that for most frequency lines, this PSD has the highest amplitude of all three, although the PSD in the X direction at some certain frequencies has a slightly higher amplitude. And if I add a coupled cursor to these displays, I can see that that bears true in the fatigue damage spectra on the right-hand side. So here, even though the GRMS value for the Z direction is about a G higher than for the X direction, I can see in this frequency region here, I have a higher fatigue damage potential in that X direction than I do in the Y direction. There's some nice little features or functionality in TestLab where I've created a little custom report here showing this same information. So this PSD dashboard display, X, the FDS, and the RMS value. And if I reject this and run this again, you'll see every time I perform this analysis, this display will automatically update with all of that process data. So I could create some nice little report displays or diagnostic displays, so I could immediately, once the data is processed, look at it, examine it, and see, okay, I'm pretty happy with this calculated data. I'll go ahead and accept this run now. One other nice thing that we can do here is we can compare these PSDs and this fatigue damage spectra to some of the standards that maybe have typically been used on the shaker table. And so I have the fatigue damage spectra from one of these ISO standards. I'll go ahead and I'll drag it into this display. I'll do it for the two other standards as well. And just for fun, I'll browse to the original data and I'll plot the PSD for one of these standards against the PSD for the synthesized test. We'll do them all. So what I can see here is my ISO 16750 standard. It has at almost all frequency lines, a much higher fatigue damage potential, except for at this frequency location here, which again, if I grab a coupled cursor, I can see at, let's say, this is a pretty small overlap region here, but 11 hertz to 10 hertz, my other standard has a higher amplitude. And so my conclusion here is if I'm looking at the X direction here on my component, that if I'm using this ISO 16750 PSD for the testing, I am using a pretty conservative approach, which can be good. Maybe that's what you desire out of your design, but maybe it also means you have a little leeway to accelerate that test further. I could also use this to say, okay, I'm looking at maybe this PSD from the two-wheeler standard here, and I can see at certain frequencies I am under testing my component. So in this region here from, let's call it 20 hertz to 40 hertz, the FDS of the measured data is higher than the FDS of the standard, and that kind of bears itself out as well if I were to look at the PSD shapes from my synthesized test. So that's here in red, and the PSD from the ISO standard. So I can see that if I'm using this blue curve here, I may be underestimating the damage potential that my component might see. And if I have some resonances in this frequency range on my component, I might be in some trouble. I might see a break in the field data that I wouldn't see if I were to just use the common standard. So it's a very good tool to compare your measured field data with some standardized PSDs that perhaps you've used. Okay, we'll hop back to the presentation. I've got two other small features to show here. So the first one is going to be this addition of variable angles for the critical plane approach when we are utilizing strain gauge rosette data. The general idea behind a strain gauge rosette is that they're very helpful in a multi-axial fatigue problem. So if we're measuring strain and we don't know the direction at which the part or the component is experiencing the maximum strain, we are able to use this critical plane approach to derive time histories at various angles. We can then cycle count those time histories either using a pseudo damage or a stress life or a strain life approach, and we can determine at which angle we're experiencing the maximum amount of fatigue damage. Since some earlier releases, we've been able to calculate angles in 10-degree increments from 0 to 180 degrees. But what we've recently added into the software is to set variable user-defined angles. So now if there's a particular angle you just historically know and understand, this is typically the angle where you see the maximum strain from your component, you can manually enter in that angle. Show that here in TestLab. Let me open that back up. I'm going to go to my newer section or new section here. I've got a section that I just call Rosette. And in this section, I have a method called critical plane 0, 45, 90 with variable angles. And I've also got a strain life method here. So in this critical plane method, look at the properties, I can choose this angle configuration. So that's one of these little ... menus here under properties. And I can enter different angular values. So in this case, we are calculating angles from 0 to 10 and then incrementing by 10 all the way up to 170. I could use an arbitrary set of angles in here. So I could say 0, 10, and I'm just going to do like 120, 125, 135, 140, 145, and so on. So this is a completely user editable field. I'll hit OK. And then I'm just going to perform a strain life analysis on this data. Let me make sure I have my Rosette data in the input basket. I don't believe I do. We'll replace that in the input basket. It's just a 3 channels from a strain gauge rosette. So a 0 channel, a 45, and a 90 channel. I'll select run here. And if I look in the active analysis results, you can see I have my angles that I've configured. So I've got 0, 10, 120, 125, 135, and so on. And I can compare the fatigue life statistics for all those channels. And so I can see at some of these angles like 0, I'm actually not computing any accumulated fatigue damage. However, at different angles on this structure, so at 120, at 125, especially at 135, 140. And 145, I'm seeing a much larger amount of fatigue damage accumulated. So what this is showing me, or what this is telling me, is that these are the primary angles that I need to be concerned with when I'm doing my multi-axial fatigue life calculations. And if I was just going to cycle count the 0, the 45, or the 90 directions and perform a fatigue life analysis there, I am under calculating the total fatigue life damage that is occurring at that particular point on the structure. The last thing to show here, I'll go back to that presentation, is this time at level 2D plot. This is a extension onto essentially to just a 1D time at level plot, which is going to show us for a 1D time at level plot the amount a time trace spends in a specific condition. So in the example that I'm using, I have a time trace that shows what gear you're in a particular vehicle. And a time at level diagram would tell me how much time I spend in each different gear configuration. A 2D time at level plot lets me combine multiple channels together in one plot. And so what I can do, for example, is I can look at how much time do I spend in a specific gear and at a specific torque level. So it gives me perhaps a little more kind of granular analysis into how much time I'm spending at a particular level in a particular configuration, whether that be a gear, a specific gear, or a specific throttle, or so on, anything that you might want to analyze. So let me hop back into TestLab. I will go to this time at level 2D section here. I'm going to show this calculation done in two different ways. So I'm just going to calculate a time at level, and then I'll calculate a 2D time at level. I have some data. It's just a torque channel, an engine tach, and a gear number, so I can display that here. On top, I've got the torque that the vehicle is experiencing. At the bottom here, I've got the gear number that vehicle is in. I'm going to run a time at level analysis, and I can choose a number of bins that I'd like to divide everything into. For this example, I'm going to keep it a default value of 128 bins. Place this in the input basket to this, and I'll select run again. There we go. So just looking at the time at level, we'll look at the gear channel and maybe the just time plot as well. Here you can see that this time at level is showing me how much time I spend in each different gear. And so if I add a single X cursor here, this plot is rotated on its side. That's why it's an X cursor rather than a Y cursor. And I can snap this to data values here as well and highlight the curve. I spent about 158 seconds of this measurement in fourth gear. If I zoom out, I could do the same thing for these other gears. So it's giving me an indication for how long I spent in a specific configuration. I could also look at that for my torque channel or my speed channel. So this is my speed channel, and really this is just giving me a nice kind of distribution for how long I spent at different rotational speeds during this measurement. And I've got a big spike here, probably at the idle speed during this measurement. The 2D time at level allows me to show, so for example, rather than just looking at this torque measurement and this gear number measurement, it allows me to look at these simultaneously. So let me click on that 2D time at level result for my torque channel. I'm going to remove this cursor for right now. And what I'm seeing in this display is I have torque on the x-axis, I have my gear number on the y-axis, and then I have the time spent in each bin on my color axis here. And so my gear trace wasn't super pretty. There's some data points and a little bit of ripple when it's going from one gear to the other. So you see a lot of small occurrence counts outside of these 8 gears or so. But if I add a single cross cursor here, and we'll snap this to the data values, I can see how much time I spent in different gears. So essentially this horizontal line here is my first gear, and I can see what the distribution of torque values were as I was in that gear. So I can see I spent 29 seconds in this torque bin. That's from roughly minus 145 to 22 Newton meters. That was the largest amount of time. But I also have some higher torque bins here that I spent I spent a decent amount of time in at first gear at this torque level. And so I can look at these different gear levels and I can see where did I spend the most time, and did I spend a lot of time in a pretty high torque region of this vehicle's life. And that might be a useful thing for me to visualize and understand when I'm doing my durability type analyses. That is all I had for you all today. Thank you very much for joining. If you have any questions, my contact information is listed below. Well, thank you very much and have a good rest of your day.